In section 9.4, we're going to be combining what we've learned in 9.1 through 3, so translations, reflections, and rotations, and we're going to make compositions of isometries using those. So first question, just to look at it real quick, we know how to make this E fit onto the E on the right just by making a translation, sliding it over there. But another way we could think of that is if I made two reflections, I would get the same result. I could reflect the E first over a line in the middle, although that would result in the E facing backwards. I could also make another reflection line that goes right through the middle of that backwards E, and that would turn it around facing the right way. So we've seen that we can combine two or more, and that could make another transformation. So isometry is going to mean, first of all, the same distance. So an isometry is a transformation that preserves distance or length. So those three that we've seen, translations, reflections, rotations, those are all isometries because those are all rigid motions. We can express all isometries as compositions of reflections. And something else we know is that the composition of two or more isometries is an isometry. So if you make multiple rigid motions, it's still going to be a rigid motion at the very end of it. So four kinds of isometries, and again, the first three we've already seen. Translation with 9.1, rotation was 9.3, reflection we saw in 9.2, and we're adding in a glide reflection, another possibility. Again, that's combining a translation and also a reflection. We're doing that a little bit in this section with our coordinate plane. So composition of reflections across two parallel lines results in a translation, so that looking back at that last question, I could make a translation by making two parallel reflections, so I had two vertical reflections there. And we can write this composition in shorthand as a reflection over M after a reflection over L of that triangle ABC results in a triangle ABC with double prime because I've made two movements. So a little bit harder to see that triangle in the middle there, but I can make two reflections, again, instead of a translation. If I reflect a figure once over line L, and then reflect that again over line M, that result from start to finish as a translation. So again, they are parallel, those lines of reflection, that's going to make a translation. If I have reflection lines that are not parallel, so if I make reflections across intersecting lines, that would instead result in a rotation. So similar sort of terminology I can say for that. So again, reflection over M after a reflection over L with this triangle ABC is going to result in my double prime figure. So if I make a reflection over L, that gets us, again, which is kind of hard to see on this, but results in our first image. Reflect that again over line M, which intersects line L, and that would result in a rotation from first to third figure. So any composition of isometries can be represented by either reflection, translation, rotation, or a glide reflection. So those four we saw on the last page. Glide reflection is a composition of a translation, or that's the glide part of it, followed by that reflection across a line that's parallel to the direction of translation. So you see on the last page, I can move something and then flip it over a reflection line. You can map a left paw print onto the right paw print using that glide reflection. So we're going to be practicing making a couple of rigid motions at once. So this looks like a reflection after a translation of triangle TEX. So first thing you want to do is put those coordinates in -5, 2, -1, 3, and -2, 1. So T, E, and X, we have that triangle in the second quadrant. And doesn't actually matter which order you do these in. If you're going from start to finish, you're going to end up the same way. But starting with that translation, if I go translating 0, -5, remember that's translated 0 units to the left and the right, but 5 units downwards. So my first image would result in T prime, E prime, X prime, which is that triangle moved down 5 units. So every point moves down 5. And then if I also want to reflect that over the line X equals 0, that's also another name for the y-axis. So if I take this image, reflect that over the y-axis using the strategy we saw in 9.2, so count over the same amount on both sides, I would get this final image, so T double prime, E double prime, X double prime. That would be in that fourth quadrant there. So I can move something, I move that triangle downwards and then reflect it. That would be a composition. So trying that a little bit further, we have this triangle TEX again, so same coordinates to start with. This time we want to reflect it over the line y equals -2 after we've translated it using the rule 1, 0. And again, reading that rule 1, 0 means I move 1 unit in the x direction, so 1 unit shifted to the right, so it doesn't change too much the first time. But then if I follow that with a reflection over the line y equals -2, First thing you have to remember is that y equals -2 is a horizontal line through the y value of -2. And if I use my rules again for reflections, I reflect my points from my image, and that gives us a second image. So my final position of that triangle is going to be a little bit lower because I reflected it over that horizontal line. So 9.5 is also pretty similar. We're using the same types of movements, but this time we're calling them congruence transformations. First question here is asking us, if I get this picture in a book, if I draw a line, fold it over a piece of paper, and then trace it again, we know that both wings are identical because we know it's a reflection, and reflection is going to preserve the same size and shape because it's a rigid motion. So any type of reflection that we do, those should be congruent figures, and that's what we're going to be using to prove things are congruent. So two figures are congruent if and only if there's a sequence of one or more rigid motions that maps one figure onto the other. So that first example was just one motion, just one reflection, although from 9.4 we could combine a few at once and that could still be a rigid motion. So we're going to use that to figure out which pairs in these coordinate planes are congruent, and we're also going to decide on what kind of rigid motions we can use to map one onto the other. And you could use the notation that we saw before in 9.4, but I also just kind of described this in terms of general terms, how we're going to move one to the other. So first thing I noted was that these trapezoids, ABCJ and WXYZ, those are going to be congruent. And we can get from one to the other. I said we could take ABCJ, reflect that over the y-axis, so it'd end up in this area. And if I translate that left 1 unit and up 5, that would fit right over that second trapezoid, WXYZ. So again, they're going to be congruent if I can take one figure and move it in a way that fits directly over the other figure. So second congruency that we find is those two triangles, DEF and LMN. Those are going to be congruent. And you could find either one by rotating them 180 degrees. So 180 rotation, we'll put one onto the other, that would be congruent. And last we see that these segments are also congruent. And we can tell the segments are congruent, kind of like that last one. We don't have to do multiple transformations, just a simple translation downwards starting from PQ. So it looks like 2 to the right and 9 downwards is going to line up the points from P over H, and 2 to the right, 9 down. That'll line up Q over G. So those would be congruent. So same thing on the next one. If we want to see if those two rhombuses are congruent, I can translate ABCD, right 6 and down 5, so that would just be a direct translation. I can just slide that over. For the triangles, though, it looks like it'd take a little bit more, so I could start with triangle UVW, translate that 6 units to the left, so it'd fit it right over this triangle that we're trying to prove is congruent. And then if I reflect that over the x-axis, that would fit over that figure. So again, sometimes you might have to do more than one movement. We'll see that on the next page with those examples, but to fit those triangles, I would have to move and then reflect, so that would be a glide reflection. So trying that a little bit more with some specific examples, this diagram we want triangle JQV to be congruent to triangle EWT, and again we can call those congruence transformations because I'm proving that they're congruent by fitting one over the other. So if I want to map JQV onto EWT, there's a couple options for this. There's never one way that you have to do these, again, because you could use reflections, rotations, translations. But using my notation, I said that we could move this first translated 5 units upwards. So I took JQV, I moved every point 5 units up. That brings us to the first quadrant. And then it looks like these are mirror images of each other, so that I could then reflect my image over the y-axis. That would result in the triangle we're looking for. So again, if I translate 5 units upwards and reflect in the y-axis, that would map JQV onto EWT. And last one there, if we want to get from triangle NAV to BCY, first thing we could do, just like the last one, is slide NAV 5 units to the left. That's going to line them up so they look like mirror images. So I can start with a translation of left 5 units. And then this time, if I reflect in the x-axis, that would line up all of my points over the points in that third quadrant. So if I do a translation followed by a reflection, so a glide reflection, that would map NAV onto BCY. And last question, pretty straightforward, but it's just asking if those figures are congruent. First, we can tell that A can be proven as congruent to B because it would just take a translation to move this sun figure over the second sun figure, and cover up that figure exactly. So simple translation would result in those being congruent. Although for part B here, since they're a different size, we know that there's not going to be any kind of rigid motion that would change the size. So we know they're not congruent because no congruent transformations can move one star and completely cover up the other one. So even if I'm using a translation, reflection, or rotation, there's no way that I can prove those are congruent. So make sure we have these complete, and again, come in with notes for tomorrow.